I will wait 5 more minutes, then I will start. Hello everyone, I am Honar Gup, a PhD scholar at IIT Kanpur. I am TA of the course Fundamental of Supersonic and Hypersonic Flow. Today we will discuss what was taught in the week 3, and if you have any doubt you can ask. And if you have any doubts regarding the course also, you can ask that also. So we will see what is waves. Wave motion can be thought of as transport of energy and momentum from one point in space to another without the transport of matter. So if one wave is moving from one space to another, so it is mainly transporting the energy and momentum. If you have solved the normal shock also, you might have seen that if normal shock is moving, then its energy will, let's say this flow is here at rest equal to 0, and one shock is moving here, then velocity behind this shock will increase. So it means that its energy and momentum is increasing. So the shock can be seen as a transport of energy and momentum. In mechanical waves, that is water waves, waves on the string or sound waves, the energy and momentum are transported by means of disturbance in the medium, which is propagated because medium has elastic properties. The disturbances are propagated because medium has elastic properties. And these waves we can define using the partial differential equation, and the generalized form of second order partial differential equation can be written as A dou 2 phi upon dou x square plus B dou 2 phi upon dou x dou y plus C dou 2 phi upon dou y square equal to S. So this partial differential equation can be of three types, and the type of partial differential equation we can find using this coefficient A, B and C. So if we find the value of b square minus 4ac, then we can find which type of partial differential equation it is. If value of this b square minus 4ac is greater than 0, then it is hyperbolic equation, and it will have two real characteristics. If b square minus 4ac is equal to 0, then it is parabolic equation, and it will have one real characteristics. And b square minus 4ac is less than 0, then it is elliptical equation, it will have no characteristics. And the characteristics are the path through which information is propagated in the solution domain. So let's see one example. There is equation 1 minus m infinity square phi xx plus phi yy equal to 0. Here phi x-axis is dou 2 phi upon dou x square, and similarly phi yy is dou 2 phi upon dou y square. This equation is for 2D velocity potential equation for steady, inviscid and isentropic compressible flow past a cylinder body. So in this equation you can see that if you compare with this general equation, you can see that value of A is 1 minus m infinity square, value of B will be 0 because there is no dou 2 phi upon dou x dou y term, and value of C is 1, coefficient of dou 2 dou to phi upon dou y square. So if we find the value of v square minus 4ac, it will be minus 4 1 minus infinity square. So when will be the value of this? When its value will depends on m infinity, because m infinity can be any value. If m infinity is less than 1, then this term will be positive and this whole term will become negative. So if b square minus 4ac is negative, then it will be elliptical partial differential equation. If m infinity is equal to 1, then this term will become 0. Then the equation will be parabolic. But the thing is that this equation, when it was derived, it was mentioned in the class, you might have noticed that this equation is not valid near Mach number close to 1. So we cannot use this equation at m infinity equal to 1. And for m infinity greater than 1, this term will be negative and this whole term will become positive due to this negative sign. So b square minus 4ac will be positive. So equation will be hypersonic partial differential equation. This equation is also not valid for m infinity greater than 5. For hypersonic flow, it is not valid. So we'll focus on hypersonic flow because waves motion are generally given by hypersonic partial differential equation. So let's say there is hypersonic equation. So it will have two characteristics line. These two are characteristics line. One is going in positive moving forward, and there is another characteristic line which is moving backward. And this is the spatial domain 0 to L, and this is the time domain 0 to T. So we are moving forward in time in this direction. So if we see one point P xt, then the solution at this point will be dependent on all these values, whatever is here. All this region will affect the solution at this point P. So this region is called the domain of dependence, the domain on which solution at one point depends. And this point will affect the solution of whatever is situated here in this region. So this region is called zone of influence. We can see this domain of dependence and influence for elliptical and parabolic equation also. For elliptical, there is no real characteristics. So at any point P xt, its solution will depend from everywhere, and it will also affect the solution of everywhere. So its domain of dependence is this whole domain. And for parabolic partial differential equation, it is similar to marching problem. Like if there is one point P, then its solution will depend of whatever in the time domain, whatever has happened before, it will depend on that. So this is called the domain of dependence. So it will have only one real characteristics line, which is this line. And above this will be the domain of influence, zone of influence. The solution of any point after this will depend on this point or whatever has happened before that. There are some characteristics of hyperbolic partial differential equation. So these equations are mainly, you will see these kind of equation in wave propagation or vibration problems. And the hyperbolic problems are initial boundary value problem. We can accommodate the discontinuity which are present in the flow by this equation, like shock waves. You might have seen before also that shock wave is nothing but gas dynamics discontinuity. If there is one shock wave, then across it properties changes suddenly. That's why it is called a discontinuity. Compressible flow at speed close to and above the speed of sound exhibit shock wave, and implicit flow equation are hyperbolic at these speeds. Disturbances at a point can only influence a limited region in space, leading to zone of dependence and zone and influence. You might have seen that here the solution at one point will affect only a limited region in the space, not the full space. So that's why there it makes some zone or influence and zone of dependence. Speed of disturbance propagation in a hyperbolic problem is finite and equal to wave speed. However, parabolic and elliptical equation accommodate infinite propagation speed. So disturbance propagation in hyperbolic problem is based on wave speed of wave. Only when wave will move forward, then only the disturbance will propagate. So we can write the wave equation as dou to u upon dou t square equal to a square dou to u upon 2x square. So it will have two characteristics. One is dou to u upon dou t plus a dou u upon dou x, and another one is dou u upon dou t minus a dou u upon dou x equal to 0. It will have these two characteristics. And if you see this characteristics, dou u upon dou t plus a dou u upon dou x, let's say there is one wave in space-time. It is given by this, and it has at one point it's a velocity u. So this whole wave is moving with velocity a in space-time. So dx by dt for this wave is a. Let's say there is different characteristics dou u by dou t minus a dou u by dou x. Then what will be the velocity of this wave? Velocity of this wave will be minus a, dx upon dt equal to minus a. So that's why you can see that one wave is moving forward and one wave is moving backward. So that's why it will have two characteristics. This one is moving forward and one is moving backward. And this wave equation can be solved using the numerical method, which is given by ui n plus 1 minus ui n upon delta t. This is the discretization in time domain, and this discretization is forward time discretization. You can see that at, let's say there is one point I n, so we are moving forward in time for the discretization. That's why it is forward time discretization. Plus a ui n minus ui minus 1 n upon delta x equal to 0. Here we are moving backward in space for discretization. So it is backward speed discretization equal to 0. Here this n is for time and I for space. Here we can define one parameter CFL number, which is given by c equal to a delta t upon delta x. So for stability of this numerical method, this value of phi should be between 0 and 1. This is a requirement for stability. So waves can be of two types. One is instantaneous wave and another one is finite wave. So instantaneous wave is like before we have seen, like given dou u by dou t plus a dou u by dou x equal to 0. This is instantaneous wave, and it is mainly, these kind of waves are mainly acoustic waves, and these form remain unaltered. Their form does not change, and these for these wave characteristics line are given by this. These are you can say parallel. So dx upon dt for this is a, and this wave we are showing is the right running wave. If you make the wave on the left side, it will be the left running wave, and equation will have this minus sign here. In the finite wave, there will be effect of local velocity of the flow, which comes in the picture. So the velocity of wave will be given by u plus a, and as u changes with space time and a also changes with xt, then that's why this wave will be curved. It will not be straight. So that's why these waves can be altered with time. And these waves also can combine and make a stronger wave also. Like that also we form the shock waves. So let's say we have two waves. One is this, which is called the one which is moving in, which is right running, is called C plus characteristic wave, and the one which is left running is called C minus characteristic wave. And each wave will have one compatibility equation, which is given by du plus dp upon rho equal to 0 for C plus characteristics, and du minus dp upon rho equal to 0 for C minus characteristics wave. And there are some Riemann invariant which are constant along a line. Let's say there is this line. We can find one Riemann invariant which is constant along this whole line. So for C plus characteristics, this Riemann invariant is given by j plus equal to u plus 2a upon gamma minus 1, which is constant. And in C minus characteristics line, j minus equal to u minus 2a upon gamma minus 1 equal to constant. So let's say there is one point E xt. We have to find properties at this point, solution at this point. So what can we do? We can, if we know that Riemann invariant in these two lines, we can find the solution. Like let's say we have to find the velocity u. Then you can just add these two equations and you can find u equal to j plus j minus upon 2. And if you substitute the value of u here in this equation, you will find the value of a equal to gamma minus 1 upon 4 j plus minus j minus. Like that we can find the solution at any point using this Riemann invariant. And generally this Riemann invariant also we can find using the initial and initial boundary condition. So using this method, there is one powerful method of characteristics, you might have heard about it, to find the solution of problem. So the finite wave can be in different forms, like if they are moving away from each other, then these waves are expansion waves. And if they are moving towards each other, then they will coalesce into each other and make a shock wave. How will it will happen? Because this initially it will have a small velocity, and later waves will have large velocity. So let's say there is multiple number of waves. So initially it will have low velocity and it will have large velocity. So as they will move forward, they will coalesce into each other and make a stronger wave. That's how shock wave is formed. Which is also a strong pressure wave. It is due to the slow moving wave and fast moving waves, which I told that if they are moving forward, then they will collapse to each other. And dx by dt for these waves is given as u plus a. And the wave front of this wave changes its shape as it moves forward in space-time. How can we make these strong wave? Let's say there is one piston in the tube, and if we move this piston rapidly, then what happens that initially it will have some wave which is moving, let's say velocity u1, and behind this velocity it will increase due to movement of piston, and then these all waves will join together and make the strong pressure wave. Another way for making the strong wave is, you might have seen in 3D nozzle, if this PB is between first critical and second critical point, then there will be one shock wave inside the divergent section. That's how we make a strong wave. And another wave is, let's say there is one bluff body and flow is moving with supersonic speed. Then there will be one strong shock in front of this body. Is there any doubt till now? If there is no doubt, then we will move forward. If there are any doubt from the classes also, you can also ask here. Okay. So now we will see what is normal shock. So normal shock is which shock wave we have already seen how it forms. So normal shock is also a gas dynamics discontinuity, and we derive some equation for this normal shock. So there are some assumptions which we have to take. First is that flow is steady. There is 1D flow. Flow is inviscid, and this inviscid flow is only for the upstream and downstream. Between the shock, it is very thin region and it is very highly viscous. Flow is adiabatic. There is no heat transfer, no external shaft work, and gas is calorically perfect gas. So we know the condition of the upstream, and it is given by 1. Downstream condition is given by 2. And the Mach number in upstream is greater than 1. So let's say we have one shock wave. We will take one control volume ABCD, and this region is state 1, this region is state 2. If state 1 has property P1, T1, ρ1, H1, E1, if state 2 has properties P2, U2, ρ2, T2, H2. So first we will see the continuity equation. So in integral form, continuity equation is given by dou by dou t triple integration rho dv plus double integration s rho v dot ds equal to 0. So we have taken assumption that flow is steady. So this time term, time variable term will go away. So it will be 0. So our continuity equation will remain only this part. Double integration rho v dot ds. So v dot ds we have to find for this control volume. Now we have 4 surfaces A, B, C, D. So if flow is happening in this direction, and if you see the normal of this AB surface, it is in this direction. CD surface normal is in this direction. So B dot ds for this AB and CD surface will be 0. Normal for this surface, let's say this area is A, so normal for this surface will be minus AI. And if this area is also A, then normal for this surface will be AI. And velocity this side is U1, velocity this side is U2. So we will expand this. So for AB and CD we don't need to write this. So we'll get rho 1 U1 I1 I cap for this surface. We are writing for this surface. Rho 1 U1 I cap into minus A dot minus AI cap. I dot I is equal to 1 plus rho 2 U2 I cap dot AI cap. I dot I cap equal to 1. So if we write it, rho 1 U1 A equal to rho 2 U2 A. Area is same, so we will get rho 1 U1 equal to rho 2 U2. This is the continuity equation. Now we will see the momentum equation. So momentum equation also we only need to see x momentum equation. So first let's see the momentum equation. Dou y dou t triple integration v rho ui dv plus double integration rho v dot ds equal to double integration sigma ij dot ds plus triple integration v rho f vector dv equal to 0. So this term will be 0 because flow is steady. Because our flow is steady, it will be 0. And as there is no body force, this term also will be 0. So we are left with only these two terms. Here the sigma ij, it can be given by minus p del ij dou ij plus lambda kk del kk dou u kk upon dou x kk. And because our flow is inviscid, this whole term will be 0. So we will get sigma ij equal to minus p del ij. So we will substitute all these here. And we will write the equation for x momentum equation only, because the flow is only 1D flow. So after substituting the sigma ij, our equation will come double integration rho ux. We have taken the u velocity ux, x direction velocity, v dot ds equal to minus double integration p dsx. So this area is also we are taking x direction. So similar to before, in these two surfaces AB and CD, v dot ds will be 0. So we will consider only AD and BC surfaces. So for AD surface, I will make this surface here also. So for AD surface, this is normal is minus AI, for this normal is AI. So for AD surface, rho 1, its where density is rho 1, ux is u1, v dot ds is u1i dot minus AI plus for BC surface it is rho 2 U2 U2I into A2I. For this preferred term we'll get minus P1. Here ds value is minus AI, so minus A, so it will become plus A minus P1A, sorry, plus P1A minus P2A. So if we simplify it, it will become rho 1 U1 square A plus rho 2 U2 square A equal to P1A minus P2A. A is common everywhere, we can remove it. So we will get P1 rho 1 U1 square equal to P2 rho 2 U2 square. This is X momentum equation. We will see energy equation also. So energy equation is given by dou by dou t triple integration rho e dv plus double integration rho e uj dot ds equal to double integration ui sigma ij dot ds triple integration rho q dot plus rho f dot ui dv. As it is steady flow, this term will become 0. There is no heat generation, so this term will be 0, and there is no body force alpha, that's why this term is also 0. So we are left with only these two terms. In the equation, E was given by E plus V square upon 2. And so we will substitute everything. This sigma ij we will substitute here. So our equation will become double integration rho e v dot ds equal to minus p del ij uij dot dsj. So for in the tensor notation you might have seen del ij into ui equal to uj. So we'll substitute it here and we'll get minus double integration p uj dot dsj. So we'll write this equation for all four surfaces. We don't need to write it for surface A, B and C, D because V dot ds is 0 there. And the normal for these two surfaces AD and BC is minus AI and plus AI. So for surface AD, it is this V dot ds, I have directly written it here. So we are getting rho 1 E1 plus E1 square upon 2. I have substituted the value of E. E1 plus E1 square upon 2 U1AI plus for surfaces BC it is rho 2 E2 plus V2 B2 square upon 2 U2 A2. Equal to P1, this is P1 U dot ds equal to minus A I equal to minus A. So it will be P1 A1 U1 minus P2 U2 A2. Here for surfaces AD it will be P1 U1 minus A1 and this minus minus will become plus. So this A is common everywhere, we can remove it. We will write the term for P1 u1 for the upstream one side and for downstream one side. So we'll get e1 e1 plus rho 1 u1 e1 plus v1 square upon 2. This v1 we can also write e1 also. It is same only. So here you can see that rho 1 u1 is there and rho 2 u2 is there, and rho 1 u1 equal to rho 2 u2. So we can divide this whole equation by rho 1 u1 for this side and rho 2 u2 by on this side. So we'll get e1 upon rho 1 plus e1 plus v1 square upon 2 equal to p2 upon rho 2 plus e2 plus v2 square upon 2. Now you might know that h equal to e plus pv or e plus py rho. So this we can write it as h1 and this term we can write it as h2. So we will get h1 plus v1 square upon 2 equal to h2 plus v2 square upon 2. This is the energy equation. So all equation combined we can write this as quantitative equation is rho 1 e1 equal to rho 2 u2. Momentum is e1 plus rho 1 e1 square equal to p2 plus rho 2 u2 square. Energy equation is h1 plus u1 square upon 2 equal to h2 plus u2 square upon 2. If we know every value in the upstream, like rho 1 u1, rho 1 u1, p1, h1, then we don't know anything in the downstream. So we have how many unknown? Rho 2, u2, p2 and h2. We have 4 unknown, but we have only 3 equations. So we'll use one more equation as h2 equal to cp t2. But here then t2 is unknown. So we'll use one more equation as equation of state E equal to rho RT. So these 5 combined equations will give the solution for the normal shock waves. Is there any doubt till now? So if we solve all these equations, we'll get some normal shock relations. Here m1 is Mach number in upstream e1 upon a1 and m2 is Mach number in the downstream e2 upon a2. So mt square is given by 1 plus gamma minus 1 upon 2 m1 square upon gamma m1 square minus gamma minus 1 upon 2. Rho 2 upon rho 1 equal to u1 upon u2. This is from continuity. So we'll get gamma plus 1 m1 square upon 2 plus gamma minus 1 m1 square. T2 upon T1 equal to H2 upon H1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square minus 1 2 plus gamma minus 1 m1 square upon gamma plus 1 m1 square. Pressure ratio we can find by P2 upon P1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square upon m1 square minus 1 and P2 upon P1 equal to 1 plus gamma m1 square upon 1 plus gamma m2 square, and T2 upon T1 is we can find from equation state also. There is also one more relation for the entropy, which is from the S2 minus S1 equal to minus R log E02 upon P01. So in this one, some relations are important, like this P2 or P1 relations. It is better if you know. So generally, you will know the value of M1. So you can get the P2 by P1 from here. It is better if you know this relation also, because it is easy to find M2 using these two relations than this relation. Or because it is difficult to remember also. And mainly these are the important relations. So Now we'll see some plots related to normal shock relations. On the left hand side, upstream and downstream Mach number are plotted against each other, and in the right hand side, entropy and Mach number are plotted. So first we'll see the entropy plot. So F2 minus S1 upon R versus M1. So here you can see that for Mach number greater than 1, entropy is increasing, and for Mach number less than 1, entropy is decreasing with across the normal shock wave, which is not possible because entropy always increases. So Mach number less than 1 is not possible. And if you see the Mach number plot, for Mach number greater than 1, it means if upstream is supersonic, downstream we are getting is subsonic. If upstream is subsonic, downstream we are getting is supersonic. But we already saw that subsonic upstream is not possible, so it is not possible. This is mathematical solution only. In physical reality, it does not happen. Is there any doubt till now? Okay, then we will check the oblique shock. So oblique shock are generated when flow is moving up, on the top of waves, symmetrical waves, or through a concave corner. It happens when flow is moving towards oneself. So if let's say flow is moving like this and it is moving towards oneself, then their oblique shock will form, and only when this flow is supersonic, Mach number is greater than 1. If it is subsonic, it does not happen. So it happens only when Mach number is greater than 1. So now we will see what are the assumptions which can be taken for oblique shocks. Similar to normal shock, flow is steady here, but here flow is 2D, it is not 1D, because you can also see that flow is changing the direction. If it was moved like this, then it will move like this, according to direction of the wedge or concave corner. And flow is inviscid in upstream and downstream, but not on the shock. Flow is adiabatic, there is no external software, there is no body force, and gas is calorically perfect gas. So let's say flow is moving with velocity v1 in this direction, and it is turning at angle theta at velocity v2. So we are getting one shock at angle beta, and we can resolve this velocity v1 and v2 as along the shock wave and perpendicular to the shock wave. Perpendicular velocity is given by u1 and u2, and tangential velocity is given by w1 and w2. And here we are taking the control volume as this A, B, C, D, E, F, where surface A and D are parallel to the shock wave and other surfaces are parallel to the velocity. So whenever we will take the dot product of velocity and surface, this its normal surface will be, for the x moment x velocity, it will be the 0. V dot, sorry, for velocity this v dot ds will be the 0 here, because velocity will be tangential to all these surfaces. So we have to consider only two surfaces, A and D. So we'll see the constraint equation first. Dou upon dou t, triple integration rho dv equal to double integration rho v dot ds equal to 0. So as flow is steady, this term will go 0, and for this term we will write it for two surfaces which we have seen, this A and D. Here for the surface A, density is rho 1, and velocity if you see here, you can write the velocity. Let's say this x direction is perpendicular to the shock, y direction is along the shock. So this velocity you can write u I cap plus u1 I cap plus w1 j cap. This side velocity you can write u2 I cap plus w2 j cap. And this surface is normal to the shock, parallel to the shock. So this normal, let's say this area is A, so it will be minus A I cap, and this surface normal will be A I cap. So if you take the dot product of this velocity and this surface, you will get minus ui A. Minus ui A, and here there is term also w1 j cap plus w2 j cap. So dot product will come rho 1 u1 A plus rho 2, minus rho 1 u1 A plus rho 2 u2 equal to 0. A is common here, so we'll get rho 1 u1 equal to rho 2 u2. Now we'll see the momentum equation. So momentum equation similar to before, dou by dou t, triple integration rho ui dv plus double integration rho v dot ds equal to double integration sigma ij dot ds plus triple integration rho f dv. As there is no body force, this term will go 0, and steady flow, so this term will go 0. Now we have only two terms, and sigma ij, we have before mentioned that due to inviscid flow, it will be equal to minus p del ij. So our equation is going by this. Now we will first see x momentum equation. So we are considering only two surfaces, so because rest of the surface will have v dot ds equal to 0. So for surface A, let me draw it. For surface A, it will come rho 1 u1 minus u1 a1 plus rho 2 u2 into u2 a2. Depth of surface will have v dot ds equal to 0, equal to p1 a1 minus p2 a2. You might have questioned that why for this term p we are not considering this b, f and c, e, because for this normal is this side, normal is this side, but pressure value is same. So sum of these two will be 0. Similarly, sum of these two will be 0. So we don't need to consider these surfaces for pressure value also. And if we simplify it, we will get P1 plus rho 1 U1 square equal to Pt plus rho 2 U2 square. This is X momentum equation. Till now you have seen that both equation, continuity and momentum, you are getting similar to normal form. Only difference is that we are getting the normal component in the velocity instead of full velocity. You have to know that velocity v is nothing but u I k plus w j k. We are taking only the x component here. So sorry, I mentioned one thing wrong. We are not considering this direction before for the pressure because it will be used for y momentum. X momentum will have only two surfaces A and D. Sorry for that. So for y momentum, we will write y momentum for this surfaces. So velocity will be along the shock wave. So along the surface A and D, velocity will be so v dot ds will be only along the surface A and D, which will be value will be equal to minus u1 a1 and u2 a2. And but this velocity will change because now we are considering the y momentum. So we'll get rho 1 w1 into minus u1 a equal to rho 2 w2 u2 a. And for this pressure term, as I mentioned before, that pressure value for these two surfaces are same but direction is different. So whole effect of this will be 0. Similarly for other side also. So we'll get this equal to 0. And here common is A, so you can remove it, and we'll get rho 1 u1 w1 equal to rho 2 u2 w2. And from the continuity we know that rho 1 u1 equal to rho 2 u2, so we'll get w1 equal to w2. This is y momentum equation. Now we will see the energy equation. So energy equation is given dou y dou t triple integration rho e dv plus double integration rho e uj dot ds equal to double integration uj sigma ij dot ds plus triple integration rho q dot plus rho f dot ui dv. So as our flow study, this term we can remove. There is no heat transfer, so this term we will remove. And as there is no body force, this term we will remove. So we are left with two terms only. And the sigma ij also we will substitute with minus p. Now we will expand this for our control volume. So v dot ds we are taking only for two surfaces. because only for those two surfaces only it is non-zero. So we'll get minus rho 1 E1 plus E1 square upon 2 U1 A plus rho 2 E2 plus V2 square upon 2 U2 A equal to right hand side we'll get this V dot S also for only two surfaces. We'll get P1 U1 A minus P2 U2 A. A we can remove from everywhere, and U1 you can see that rho 1 U1 is, and we can write the term with 1 at one side, 2 at two side, other side. So we'll get E1 U1 plus rho 1 U1 E1 plus E1 square upon 2 equal to E2 U2 plus rho 2 U2 into E2 plus V2 square upon 2. Now you see here is rho 1 U1, here this side is rho 2 U2, and both are equal from continuity. So we will divide left hand side by rho 1 U1 and right hand side by rho 2 U2. So we will get left hand side E1 upon rho 1 plus E1 plus E1 square upon 2 equal to E2 upon rho 2 plus E2 plus V2 square upon 2. And we know that H equal to E plus PV or E plus P by rho. So we can write E1 plus P1 upon rho 1 as H1 and E2 plus P2 upon rho 2 as H2. So ultimately we will get H1 plus V1 square upon 2 equal to H2 plus V2 square upon 2. This V1 and V2 are velocity in upstream and downstream. So V1 square equal to U1 square plus W1 square and V2 square equal to U2 square plus W2 square. And if you substitute this here, we can get H1 equal to U1 square upon 2 equal to H2 plus U2 square upon 2, because W1 and W2 are same. We can cancel it out. Any doubt till now? If there is no doubt, we can move forward. If there is doubt, and if anyone has any doubt, they can stop in between also and ask. Okay, so now we'll write all equations which we have derived together. So rho 1 U1 equal to rho 2 U2, it is continuity equation. One thing to pay attention is that our velocity in upstream was V1, downstream was V2. U1 and U2 were normal to shock wave, and W1 and W2 were along the shock wave. So continuity equation is rho 1 E1 equal to rho 2 U2, P1 plus rho 1 U1 square equal to P2 plus rho 2 square, and W1 equal to W2. These are momentum equation. And H plus U square upon 2 equal to constant is energy equation. Similar to before, we have unknown of rho 2, U2, P2, H2. So we need more equation. So we use enthalpy equation and equation of state. H equal to CPT and E equal to rho RT for calorically perfect gas. So we have 5 equations, 5 unknown, but we are forgetting one more unknown, which is beta, shock angle. We know the turn angle theta because it will depend on the weight, but beta we don't know. So we need one more equation to find the beta. So let's say we have found beta. We will see the equation for beta, but let's say we have found beta. So I will go with for the diagram first. So this is shock wave which has beta angle, and our flow was coming with velocity v1, and it went with velocity v2 at angle theta. So velocity normal to this is u1, this is v2, w1, and this angle is beta. So u1 will be v1 sine beta, and if we divide it by sonic velocity, we'll get m and 1. Because this is normal to the surface, we write this Mach number as m and 1 equal to m1 sine beta. m1 is the Mach number from this velocity v1. So we have to first find m and 1 from m1. Similarly, this component is u2 and this is w2. This whole angle is beta. So u2 will be v2 sine beta minus theta. If we divide it by a2, we will get m and 2 equal to m2 sine beta minus theta. These two are important relations. So for solving the oblique shock relation, first we have to find m and 1, which is equal to m1 sine beta. Now if we have found m and 1, then whatever relation you have seen in normal shock, there is one doubt you can ask. You can speak also, Arvind. Arvind, you can speak the doubt also. No, you are not audible. Okay, you can write the doubt then. In the previous page. Oh, this Mach number. So this A you are asking, this is the speed of sound. You might have studied before also. So if this speed of sound which I am taking for this u1 and v1 is here, this side upstream a1, and the speed of sound which I am taking for this downstream is a2, 2, and this you can find directly from under root gamma RT, because we are assuming that it is perfect. Yes, So you can use this relation also. A2 equal to under root gamma r theta. So we have found m1, mn1. So whatever relation we have used in normal solve, the same relation you can use there. Only thing is that you have to replace m1 from to mn1 in those relations. All relations are same. You can check also. You have to replace only m1 to mn1. So you can find rho 2 by rho 1, u1 by u2, and p2 by p1, and mn2. M1 you have to replace to mn1, and m2 you have to replace to mn2. So you will find mn2 here. And from mn2 you have to find m2. So I have mentioned that mn2 equal to m2 sine beta minus theta. If you know, first you have to find beta. So after you find the beta, then you have to do all these steps. Then you can find m2, and the temperature ratio you can find using the equation of state. If you know the pressure and density. Finding the beta, we have to use the relation which is called theta beta m relation, and it is given by tan theta equal to 2 cot beta m1 square sin square beta minus 1 upon m1 square gamma plus cos 2 beta plus 2. So generally in the problem we know the value of theta, which is turn angle and Mach number. So only unknown is beta, which you can find from this relation. And in many of the work you will see one theta beta m diagram which is plotted using this equation only, where x's are deflection angle or turn angle theta and shock wave angle beta, and it is plotted for different Mach numbers. So let's say you have to find one more thing, that for every value of theta and m you will get the 2 shock wave angle. For one value you can see that you will get the 2 shock wave angle, and one is for the weak shock and one is for strong shock. Generally you will find weak shock only, so you can use the weak shock solution. And let's say you have to find shock wave angle for one theta m value. So take theta value and take it to the Mach number which you have to find, and take the beta value for that Mach number. Like that you can find the beta, and then use the above step to find the solution. Now we will see the Prandtl-Meyer flow. So Prandtl-Meyer flow happens, or Prandtl-Meyer wave forms when flow is moving through a convex corner. So when flow is turning away from itself, you can see that flow is turning away from itself, then there will be the Prandtl-Meyer waves, and it is like a fan, so it is called the Prandtl-Meyer fan also, and it is made of infinite Mach waves. So all these are the Mach waves. So there are some assumptions for this which we have to take, which is steady flow, 2D flow, and flow is isentropic across this Prandtl-Meyer flow, because it is made from the Mach wave, and flow across a Mach wave is isentropic flow. There is no external shaft work, and gas is calorically perfect gas. And also this Mach number should be greater than 1. Expansion fan itself is a continuous expansion region composed of an infinite number of Mach waves bounded by upstream by mu1 and downstream by mu2. The angle of this initial Mach wave is mu1, which it makes from the flow direction, and the final wave's angle is mu2, which it makes from the downstream direction. mu1 is given by sine inverse 1 upon m1 and mu2 is given by sine inverse 1 upon m2. Let's say flow is moving with velocity v, and due to one Mach wave, the flow is moves away from itself at angle d theta, and its velocity becomes v plus dv. V plus dv because flow is expanding, so its velocity will increase. So this angle is d theta. This angle, let's say, and this is v, and this is the Mach wave angle mu. So this angle that is 90 degree, and this angle we will find at pi by 2 minus mu minus d theta. So if we use the sine law, we will get v plus dv upon v equal to sine pi by 2 plus mu upon sine pi by 2 minus mu minus d theta. And d theta can be found by under root m square minus 1 dv upon v, which can be written in terms of Mach number under root m square minus 1 upon 1 plus gamma minus 1 upon 2 m square dm upon m. And using this relation, there is one Prandtl-Meyer function is given, which is given by mu m equal to under root gamma plus 1 upon gamma minus 1 tan inverse under root gamma minus 1 upon gamma plus 1 m square minus 1 minus tan inverse under root m square minus 1. And theta is given by, theta 2 is the turn angle here, which is given by mu m2 minus mu m1. So if upstream Mach number is greater than 1 and initial condition is P1 Pt1, so after this expansion fan, Mach number will increase, pressure, temperature and density will decrease, and velocity will increase. And as flow is isentropic, we can directly use the isentropic relation for finding the temperature and pressure. So first step for solving this problem is, okay, this step will come later, so like this we can solve. And some physical trends is given by Mach number, initial Mach number, upstream Mach number is always greater than 1, temperature, pressure, density, this all decreases. And as flow is isentropic, total temperature and total pressure remain constant, and Mach number increases. So how to solve this problem? Generally we know the m1, so we can find the Prandtl-Meyer function for this m1, mu m1, and we know the relation theta 2 equal to mu m2 minus mu m1. So using this theta 2 and mu m1, we can find mu m2. Then using the Prandtl-Meyer relation for mu m2, we can find the m2. Then we can use the isentropic relation for finding the other properties of the flow. Only thing is that for solving this Prandtl-Meyer relation, we have to use the numerical method to find the value. Is there any doubt till now? So So now we will see the what happens to the relation which we have seen till now for normal shock, oblique shock, and uh, this Prandtl-Meyer wave for high Mach number limit. So high Mach number limit means that m tends to infinity. When Mach number tends to infinity, what happens to this relation? So first relation we will see, let's say there is one oblique shock and v1 is the velocity upstream and v2 is the downstream velocity, and u2 is the velocity in horizontal direction. Then u2 is given by, then u2 upon v1 is given by 1 minus 2 m1 square sin square beta minus 1 upon gamma plus 1 m1 square. We have not derived this relation, but you can also derive this also. So here let's see m1 tends to infinity. So you can see m1 is in both numerator and denominator. So we will divide both by m1 square. So if we divide both by m1 square, we will get 1 minus 2 sin square beta minus 1 upon m1 square upon gamma plus 1. Now if you see this term, if let's say m1 tends to infinity, if m1 tends to infinity, then 1 by m1 will tends to 0. So this term we will get as 0. So we will get 1 minus 2 sin square beta upon gamma plus 1. This one we can take this other side and we can take this on the left hand side. So we will get delta u upon v1 equal to u2 minus v1 upon v1 equal to minus, okay, this one we took other side. So we will get minus 2 sin square beta upon gamma plus 1. So in the hypersonic small disturbance theory, we have seen that beta is of the order of tau. As tau is nothing but dy L. D is the thickness of the body and L is the length of the body. And this sin beta is also approximately equal to sin theta for small angles. So hypersonic small disturbance theory equations are given by these equations, which you might have seen in classes. And here the thickness of body is D and length is L. And the tau is given by dy or L. So all terms are non-dimensionalized using this tau or length scale and velocity. So you will get tau in this equation also. Now we have seen the u2 for x direction velocity. Let's say there is y direction velocity v2 also. So v2 upon v1 is given by 2 m1 square sin square beta minus 1 cot beta upon gamma plus 1 m1 square. So for this also, if we divide by m1 square in numerator and denominator, so So we will get 2 sin square beta minus 1 upon m1 square for in the numerator into cot beta upon gamma plus 1. So if m1 tends to infinity, this term will become 0. So we will get 2 sin square beta, and cot beta we can write cos beta upon sin beta. So 1 sin beta will cancel, and 2 sin beta and cos beta into cos beta is sin 2 beta. So we will get sin 2 beta upon gamma plus 1. And if you see sin 2 beta is 2 sin beta into cos beta, sin beta is order of tau and cos beta is order of 1 for small angles. So it is order of tau. This is for small angle only. Now we'll see for pressure ratio. For pressure ratio, 1 plus 2 gamma P2 by P1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square sin square beta minus 1. Now let's say m1 tends to infinity. So this term will be very large compared to 1. If m1 is very high, then its square will also be very high. Its whole product will be very high compared to 1. So we will ignore this one and we will get 2 gamma upon gamma plus 1 m1 square sin square beta for hypersonic limit. And for this it will be of order of m square tau square. For small angles, rho 2 upon rho 1 is given by gamma plus 1 m1 square sin square beta upon gamma minus 1 m1 square sin square beta plus 2. If we divide both by m1 square in numerator and denominator, we will get gamma plus 1 sin square beta upon gamma minus 1 sin square beta plus 2 upon m1 square. So for m1 tends to infinity, this term will remove, and we will get sin square beta in both numerator and denominator, which we can cancel out with each other, and we will get rho 2 upon rho 1 equal to gamma plus 1 upon gamma minus 1. So one thing to note is that for hypersonic limit, very high Mach number, rho 2 and rho ratio of density across a oblique surface will tend to a constant value, which will depend on gamma. For let's say gamma equal to 1.4, if you put it here, you will get rho 2 by rho 1 equal to 6. So you can roughly say that for high Mach number, this ratio is 6. For temperature ratio, T2 by T1, it will be, you can simply give by ratio of density and pressure. Density of pressure and ratio of pressure and density. So you will get 2 gamma upon gamma plus 1 into gamma minus 1 into this gamma plus 1 whole square m1 square sin square beta. This will be for temperature ratio. Now we will see for Cp, coefficient of pressure. So Cp is given by P2 minus P1 upon half rho V1 square, which can be written as 2 upon gamma m1 square P2 upon P1 minus 1. How do we got this? Because let's say B1 square is given by m1 square into a1 square. a1 is speed of sound, and a1 square is nothing but gamma T1. And if you multiply it by rho 1, then rho 1 V1 square will be m1 square gamma rho 1 R T1. Rho 1 R T1 is nothing but pressure, P equal to rho R T, because P1 equal to rho 1 R T1. So we will get gamma P1 m1 square. So we can substitute it here, gamma P1 m1 square. P1 we have divided P2 minus P1 by P1. So we get the ratio P2 upon P1 minus 1. This P2 upon P1 we can substitute from the relation. which is 2 gamma upon gamma plus 1 m1 square sine square beta minus 1. There is also one more minus 1, but we have neglected it because so we are directly using for high Mach number relation, which is 2 gamma upon gamma plus 1 m1 square sine square beta, and this minus 1 is this minus 1. I think this is minus 1 is this minus 1. As this value is very higher than this value minus 1, we can neglect it. This m1 square will cancel from this m1 square, gamma will cancel, and we'll get 4 upon gamma plus 1 sine square beta. If you have studied Newtonian theory in the class, you might have also seen that Cp value from the Newtonian theory is given by 2 sine square theta. Here the difference is that we are getting 4 upon gamma plus 1 instead of 2 and sine square beta instead of theta. Keep note of these differences. We'll see how we can check that what is the difference here. We'll see the simplification of one more relation, which is theta beta m relation, which is given by tan theta equal to 2 cot beta m1 square sine square beta minus 1 upon m1 square gamma plus cos 2 beta plus 2. So for in numerator and denominator divide by m1 square, so we'll get 2 cot beta sine square beta minus 1 upon m1 square upon gamma plus cos 2 beta plus 2 upon m1 square. When m1 tends to infinity, these two terms will go to 0. And this cot beta we can write as cos beta and upon sine beta. So if we remove this term, then we will get tan theta equal to 2 cot beta sine square beta upon gamma plus cos 2 beta. This cot beta we can write as cos beta upon sine beta. 1 sine beta will cancel, and 2 cos beta and sine beta will become sine 2 beta. So for very small angle, we can write tan theta equal to theta sine 2 beta equal to beta and cot 2 beta equal to 1. So we'll get theta equal to 2 beta upon gamma plus 1. And so we'll get beta upon theta equal to gamma plus 1 by 2. When gamma equal to 1.4, beta equal to 1.2 theta. So one thing to note is that beta value is equal to 1.2 theta for high Mach number. So if Mach number is very high, it means that beta will be 1.2 times of theta. So for a small Mach number alpha, we can roughly conclude that beta will always be greater than this value. So rough value you can get for beta using this relation for a smaller Mach number. High Mach number, it just will be almost equal to this value only. So one more thing for this relation, if gamma equal to 1, then beta equal to theta. Okay, and here Cp value which we have found here, if gamma equal to 1, we had put the gamma value equal to 1, then we will get Cp value equal to 2 sine square beta and beta equal to theta. So this will be equal to 2 sine square theta for gamma equal to 1. So these two relations, you can see this relation is same as from the Newtonian theory. So when Mach number tends to infinity and gamma tends to 1, this Newtonian theory predict Cp value very perfectly. Now we will see one parameter which is called hypersonic similarity parameter, and it is again by product of m1 and theta. So till now in many relations what we are considering that m1 is very large, m1 tends to infinity, and theta is very small. But now uh, we will consider that m1 is very large, but it is not infinity, it's still a finite value. Okay, so theta value, wait, let me come to this relation first. So let's say theta is small, so tan theta is equal to theta, tan beta equal to beta, and sin beta equal to beta, and cos beta equal to cos 2 beta equal to 1. So if you substitute all these values here, we will get theta equal to 2 upon beta, because cos beta equal to 1 upon tan beta, which will equal to 1 upon beta. For 2 upon beta, m1 square, beta 1 square. As this value is very greater than 1, that's why we have neglected this 1, upon m1 square gamma plus 1. 2 also is neglected here. And m1 square will cancel, beta 1 will cancel. So we will get 2 beta upon gamma plus 1, which was relation which we found before for m1 tends to infinity. Now, if this m1 is not infinity, then we cannot ignore this minus 1 and 2. Because product of this m1 and beta can still be not very larger than 1 and 2. So we'll keep it here. Now take the cross multiplication. So if you do the cross multiplication, we'll get this equation: m1 square gamma plus 1 upon 2 beta theta plus beta theta equal to m1 square beta minus 1. Now we can divide this whole equation by theta square, m1 square theta square. So we'll get the equation beta upon theta whole square minus bracket gamma plus 1 by 2 plus 1 upon m1 square beta upon theta minus 1 upon m1 square theta square. This m1 square theta square is written by k square. M theta is k, similarity parameter, so it is written by k square. So now this is a quadratic equation beta by theta. So we can find the value of beta upon theta equal to gamma plus 1 upon 4. This is a quadratic equation. So you can see that minus b plus minus under root b square minus 4ac upon 2a. So like that, this is the equation which can be found. There is one mistake here, this is plus sign. Here if, one more thing, if m tends to infinity, then this k will 1 by k will become 0, and if we take the under root of this, we will get beta upon theta equal to gamma plus 1 by 2, which is similar to before relation. So this is mainly we use when Mach number is very high but finite and angle is small. So similarly, all relations for P2 by P1 Cp we can find in terms of this k value. Hypersonic similarity parameter. So what is the significance of this? parameter. Let's say we have two wedges with angle 3 degree and 6 degree. On one we have flow with Mach number 10, other we have flow with Mach number 5. So if we find m1 theta for first wedge, then we will get this 3 degree. If we convert it to radian, it will be 3 pi by 180. So this m theta, we are using theta in radian. For this 6 degree also, it will be in radian. So we will get 30 pi upon 180 for this one, m theta. For this one, we will get 30 pi upon 180. So both K1 and K2 are equal. So flow will be similar on these both stages. So that is the significance. You can see that if K value is same, we will get the similar pressure ratio, similar Cp value, similar beta upon theta. So like that, flow will be the similar. Now we will see expansion wave relation for high Mach number. So we have this Prandtl-Meyer function under root gamma plus 1 upon gamma minus 1, tan inverse under root gamma minus 1 upon gamma plus 1, m1 square minus 1 minus tan inverse under root m square minus 1. So if Mach number is very high, then this 1 we can ignore, this both 1. And here this tan inverse under root m square will become tan inverse m. And here also this m we can take out from the inside of under root. Now from the expansion of tan inverse x, tan inverse x can be written as pi by 2 minus tan inverse 1 upon x. And expansion of tan inverse 1 upon x is given by 1 upon x minus 1 upon 3 x cube plus 1 upon 5 x to the power 5 and so on. So if we put this, we find for this tan inverse m and tan inverse this under root gamma minus 1 upon gamma plus 1 m, we will get tan inverse under root gamma minus 1 upon gamma plus 1 m equal to pi by 2 minus under root gamma plus 1 upon gamma minus 1 by m. Similarly for tan inverse m equal to pi by 2 minus 1 upon m. We are neglecting all the higher order terms because m is already very large. So 1 upon m to the power n will be almost 0. So nu m will be equal to pi by 2 under root gamma plus 1 minus gamma plus 1 upon gamma minus 1 upon m minus pi by 2 plus 1 upon m. And so if we wanted to find the theta, which is nothing but difference of nu m2 minus nu m1, we can do the subtraction of both and we'll get the 2 upon gamma minus 1 upon m1 minus 1 upon m2. And rest of the properties like m1 upon m2 and p2 upon p1, we can write in terms of similarity parameter. Here the similarity parameter is given by m1 into this theta, which is tan angle, which is similar to before. So is there any doubt till now? Or any doubt in the class or any doubt for today's session? If there is no doubt, then we will this PDF I will upload in that drive. You can see the link of the drive where you find the link of this recording of this video. You can find the link of this PDF also there. Okay, so we will stop the class here today. Thank you.